Hello, students. Very good afternoon to all of you. Welcome back to Coordination Chemistry at LNT College Multimedia Studio, Muzaffarpur. Okay, so today I have brought a special topics that is metal chelates in coordination chemistry. Okay, so here uh, how the chelates are important and how the structure and composition of the chelates affects the coordination chemistry. So that actually I will illuminates in this particular video lectures. Okay, so let us talk about the metal chelates. What is metal chelates? As you know that in the Burners theory, what you have studied is that once the metal ion form complexes with ligands, right? So ultimately formation of the coordination compound or complex compound. So depends on the nature of the metal cation or the nature of the ligands. Ultimately, stability of the metal complex can be obtained. So here we have actually selected a particular topic, that is chelates, right? So chelates actually it came from Greek words, that is chile, Chele, chile means clause, ring structure, ring structure, CLAWS, class type, right? So once the coordination compound forms, so they have a ring structure, and ring structure actually uh, forms because of availability of more than two donor centers. Okay, so ligands having more than two donor centers and simultaneously it can bind a particular metal cation to form a ring like structure around metal cation is known as actually metal chelates. So this is a special type of coordination compounds actually. So chelates are the substances having more than two donor centers, or you can simply say that chelating ligands, they are a special type of ligands having multiple donor sites, and at a time more donor centers actually capture the same metal to form a multiple bonds, and during the formation of multiple bonds they can form a ring like structure, right? So here we have shown that this is the Mn plus, right? So metal in the particular oxidation state, that is n is equal to 0, 1, 2, 3, 4, like that. It may be also minus oxidation state also. So whatever oxidation state that is suitable for the metal cation, so that prefers actually a specific ligands, right? So here we have shown various examples which act as a chelating ligands, right? So chelating ligands are very special class of ligands in the coordination chemistry, right? So this is actually ethylene diamine. Look at this structure, right? So this is ethylene diamine, which is in the abbreviated as EN, right? In the short form, it is actually denoted as EN. Here, two functional group, that is NH2, right? So this is also NH2. It has also a lone pair and it has also a lone pair. So here two organic functional group, that is amine. So that will act as a donor sites, right? So once a metal comes closer to this particular chelating ligands, right? So suppose we have a M, right? So this M is the metal in a oxidation state N plus. So ultimately they can coordinate to this metal cation. So this forms a ring-like structure including metal, right? So this is ring-like structure, right? So 1, 2, 3, 4, 5. 5 members ring. It forms actually 5 membered rings, right? So ethylene diamine once react with a particular metal, it forms 5 membered rings, right? While unidentate ligands or non-chelating ligands actually forms no ring structure, right? So here two functional groups actually it forms two coordinate covalent bond with that particular metal, right? In this structure, this is the oxalic acid OX, right? So oxalate, this is oxalic acid. Here two acidic groups, that is C double OH and that is C double OH. So after deprotonation, right, minus 2 H plus, right? So two hydrogen ion they are removed from these two acidic groups. Ultimately, formation of the dianion, right? So this is oxalate ion, C double O minus and C double O minus. So here two oxygen anion will act as a coordinating donor site, right? So it also forms ring-like structure. So you can see here that is C C double bond O and that is O minus, and this is O. So once the metal cation comes in a close proximity with this kind of particular anionic ligands, two donor sites ultimately form a bond, result in the formation of ring structure 1, 2, 3, 4, 5. Again, 5 membered ring structure, right? So in this metal chelates, actually ring structure formed, and the ring structure forms which gives maximum stability to the complex, right? So this is uh, oxalate ion that forms ring structure around this metal cation, right? Another example, that is uh, glycine. This is your glycine. Here one acidic group, that is C double OH, and one functional group, that is amine NH2, that forms a complex, so that is H2C C double OH NH2, right? So after deprotonation, right, CH2 C double bond O minus and this NH2. So it has a pair of electrons and this is anionic oxygen donor. So because of two donor sites available on this particular structure, so they also donates its lone pairs to a metal in a particular oxidation state to forms a ring-like structure. So here again 1, 2, 3, 4, 5 membered rings. 5 membered rings. So here all the ligands they are acting as a chelating ligands because of presence of two donor sites, and that ultimately forms a ring-like structure. Okay. So again, this is your 8-hydroxyquinoline, right? So this 8-hydroxyquinoline, that is this OH, and this is your 8-hydroxyquinoline. It has a pair of lone pair electrons. This is a acidic proton, and after deprotonation, this will gives a structure like that, O minus, right? So here one metal comes N plus, it forms a structure. So 1, 2, 3, 4, 5. Again, this is 5-membered ring structure. 5-membered ring structure. It means once the chelating ligands come to the close of a metal cation, it forms ring structure. So they are called metal chelates. Okay. So all are called metal chelates. One most important ligand, that is EDTA, right? So EDTA has actually 2 nitrogen donors, right? So because of presence of lone pair, so 2 coordinating donor centers, that is nitrogen, nitrogen, and 4 acidic groups, that is COOH, right? COOH. Okay. So after deprotonation, it means if 4 hydrogen ion is removed from the structure, then it is converted into EDTA4 minus. Now, this particular structure has actually multiple donor centers. It means there are 4 oxygen anions acting as a donor centers and 2 nitrogen coordinating group, nitrogen coordinating centers will act as a donor centers. So ultimately it has 6 donor centers, right? So one particular ligand actually forms complexes, that is EDTA especially used in the estimation of actually magnesium, calcium and iron in the wastewater also. So it can forms very stable complexes with Ca2 plus, Mg2 plus, right, Fe3 plus, okay, zinc 2 plus. So all these metal cation forms stable complexes with this particular ligand, that is 4 minus. So this EDTA are actually Ca and CH2, CH2 and, right. So CH2, C double O minus, CH2, C double O minus, CH2, C double O minus, CH2, C double O minus. So this actually, this is one oxygen anion donor, this is second oxygen anion donor, this is third anion oxygen, and this is four oxygen anion donors, and this is one nitrogen donor, and this is second nitrogen donor, right? So this has a cage like structure, so it can capture this. Suppose we have a calcium 2 plus, right? So this forms complexes with that, right? So this in this way, so this is and this is, right? So ultimately it forms a ring like structure, 1 2 3 4, right? 4 membered rings, right? Or here also you can say 1 2 3 4 5, 5 membered rings and 4 membered rings also. Here in this case 1 2 3 4, 4 membered and 5 membered rings, right? So this EDTF4 minus actually forms 4-membered and 5-membered ring structure around this calcium 2 plus. So because of the formation of the ring structure of different sizes, so it has actually large thermodynamic stability. Okay, so all chelates are actually stable, and they are actually uh, used in a various applications. So another example, that is DMG. So it has two acidic groups. Okay, so these acidic groups actually deprotonated. So after deprotonation, it will receives oxygen anion, and this is oxygen anions. So this DMG also forms actually nickel 2 plus. So this also attains a ring structure. So nickel DMG complexes are actually ring like structure, so that has maximum stability. Now so this is so once this forms, now you can see here, you can see all metal chelates are thermodynamically stable, right? So thermodynamically stable means through the relation of thermodynamics, delta G naught is equal to delta H naught minus T delta S. Delta G change in gives free energy at standard state, and change in enthalpy at standard state. T is the temperature, delta S is the entropy of the at standard state, where delta G is equal to minus RT ln K. K is stability constant or formation constant, you can say. So greater the value of K, higher will be stability of the uh, metal chelates. So larger the value of delta G, right? So greater the value of delta G in a negative quantity, so greater will be stability of the complex. So here one most important point that should be noted, that the formation of the ring structure does not mean that all the ring structures appears as a stable forms. No, because it decide actually it is depends on the value of log k. So here 1, 2, 3, 4, 4-membered rings are formed, but log k value is very small for this structure, right? So here two amine donors acting as a coordinating groups for this cadmium, right? For same cadmium, there is 1, 2, 3, 4, 5, right? 5-membered rings forms. Here log k value is very 5.7. So it has very high stability constant, that is 5.7. Here it is very small. For this structure, so this is 1, 2, 3, 4, 5, 6. So 6-membered ring, right? 6-membered ring, but it has very low, not very low, but comparatively, this structure, it is low, 4.7 log K value. So this is less stable compared to this. Here again, the size of the ring increases, right? It means stability constant decreases. So one particular kind of ring structure is favorable for a particular metal cation. So H ring structure is not stable equivalent, right? So the ring structure only is stable that have very high log K value. Okay, so thermodynamically, and they are favorable. So because of the um, stability constant. So in this actually example, you can see this is tetra aqua cadmium complexes, right? So here 4 methylamine molecule reacting to form, this is 4 coordinated around the CD 2 plus, here 4H2O. So in the product side, actually 5 moles, 4 mole H2O and 1 mole of the complex, total 5 mole, right? So here also 4 mole and 1 mole of this, right? So 5 mole in the product side indicates that the entropy of the complex formation tendencies increases. So larger the value of entropy, so that means there are uh, independent products, more number of independent products, and the stable products, that is complex, which is formed, right? So this is the way by which chelate can be understood. Now another terminology. So this is 8-hydroxyquinoline, right? So it can forms easily complexes with aluminum 3 plus, right? Aluminum 3 plus. So to form a gelatinous white and gelatinous precipitate, right? So but once we just add here CH3, right, then it forms complexes but less stable compared to this because of the steric factors. So once this CH3 group is attached to the second position, they actually uh, creates crowding effect in the structure. So the stable complexes may not be obtained. So it is the structure, function group and substituents and donor sites that decides the actually formation of the chelates and stability of the complexes. Okay, so chelates chelates are actually ring structure, right? दूसरी second things, multiple donor sites, entropy driven complex compounds, right? And the stability of the metal chelates are very high. It means the formation of ring structure actually dictates that they have a very high bond dissociation energy, right? So compared to unidentate, suppose we have a unidentate ligand like ammonia or H2O, right? So they form complexes CO and NH3, 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 NH3. So this cobalt 3 plus, right, forms octahedral complexes having 6 ammonia molecule, 6 NH3, 6 bond, right? 6 bond, that is coordinate covalent bond. But once this forms CO3 plus with N, right? So right. So here 3 bidentate ligands actually forms chelate complex around this cobalt 3 plus. Here also 6 bond, but 3 ring structure forms, ring structure. So larger the ring structure, larger will be stability of the metal chelates or complex compound. Here no ring formation, simple 6 directional bonds are formed, so they are not much more stable compared to this analogous. So metal chelates are highly stable compared to non metal chelates, right? So in the nature, you can also see in the biological systems in human beings, what happens actually in hemoglobins. You see that is hemoglobins. Hemoglobins acts as a oxygen transport, right? So here this N, N, N. So this forms ring-like structure around this Fe2 plus, right? So this is iron porphyrin complexes having 4-ring structure that gives the stability to the hemoglobin, and it will act as a oxygen transport. In case of chlorophyll, so magnesium is also form a ring structure with nitrogen donors, right? So that actually gives maximum stability. So in nature, you can see that chlorophyll is used to photosynthesis for in the green plants, and hemoglobin will act as a oxygen transport medium for the biological system. So from the point of view, chelates are very important for the estimation of the metal cations, or actually separation of the metal cations. If you have a radioactive metal cations in our body, then the chelating ligands can remove the toxic metals from bodies also. And in the quantitative estimations also, chelating ligands are very important because they can easily form complexes, stable complexes, and precipitate it out. And so this is the way by which we can give a overview about the metal chelates, and that chelates actually important to understand the coordination chemistry further. Okay, so thank you students for overview.